Physical Science, Module 15D, we'll be talking about refraction. Our vocabulary will be the actual definition of refraction, and we'll also talk about fiber optic cables. So let's just do a review of what we learned in the last video. Reflection is the change in direction of a wavefront at an interface between two different media so that the wavefront returns into the medium from which it originated. And your On Your Own problems asked you to shine what would happen if you shined a light ray onto a mirror, and they wanted to know where the light would eventually hit. We show here that the light would bounce from one mirror to the second mirror and then back to a screen. So this is the process of reflection. And when it does change direction, it changes direction at a point where there is a perpendicular to the surface that is reflecting off of. Refraction is the bending of a ray when it passes at any angle from one medium into another, in which its speed is different as when light passes from air into water. A good example is experiment 15.3. You should probably stop the video and take a look at that and then come back. Experiment 15.3 is an introduction to light encountering a transparent obstacle. The experiment verifies that some of the light will pass through the obstacle. The experiment shows that some light can be reflected and refracted at the same time. The fact that light rays bend when they are refracted is a general rule of physics. So if a line is drawn perpendicular to the surface the light ray strikes, refracted light will bend toward that perpendicular line if light travels slower in the new substance than in the old substance. If the light travels faster in the new substance than in the old substance, the light ray will bend away from the perpendicular line. And this is the actual notes you should have for this process. And once again, when light refracts into a substance in which it must slow down, the ray will bend towards a line perpendicular to the surface. So when it slows down, it will bend towards the perpendicular line. When light refracts into a substance in which it speeds up, the light ray will bend away from a line perpendicular to the surface it strikes. So it slows down towards, speeds up, bends away. Here's an example from your text, figure 15.6, the refraction of a light ray. And this actually demonstrates with the flashlight what happens. This is a container with water, and the light is, the flashlight is pointed towards the container, and here is a perpendicular line. A reflected ray actually bounces off the container. Refracted light passes through the retainer to the other side, and you see another perpendicular line, and the refracted ray actually bends again, and another reflected ray bounces off into the water of the container. So the light strikes the surface of the water, part of the light's reflected and refracted. The part that is refracted bends toward the perpendicular line because light travels slower in water than in air. So when the light strikes the surface of water this time, on the second time, part of the light is reflected and refracted. The refracted ray bends away from the perpendicular line because light travels faster in air than in water. So here's the perpendicular line, and the ray is actually bending away from it. In this case, here's the perpendicular line, and the ray is bending towards it. So if it had traveled in a straight path, it would have gone down this way. But because it was slower in water, it bends up towards that perpendicular line. The refraction of light can cause optical illusions. And here's an example. When you see what looks like a puddle of water on a hot road, this is called a mirage. This is something we've all experienced. And to demonstrate this, we're going to stop the video and read experiment 15.4 and then come back. Experiment 15.4 demonstrates the angles of refracted light. Because light rays travel faster in air than in water, they are bent away from the line perpendicular to the water. The light rays are bent toward the person looking at the bowl with the quarter. So we had an empty bowl, and then later we filled it full of water. We had a quarter at the bottom of the bowl. Some of the rays travel above the eye line when there's no water in the bowl. So this person's looking into the bowl, and the reflected ray travels above the bowl towards your eyes. The reflected ray never made it to your eyes because it actually went too high. Because the light rays were either stopped by the bowl or traveled above your eyes, no light reflected off the quarter made it into your eyes, so you don't see it. However, in the second part, with more water, you can see there's more water in the bowl. Now there's more surface to reflect off of. So because the light rays were refracted coming out of the water, they were actually bent. The light rays that normally would have traveled above your eyes were bent towards your eyes, and then you could see the quarter. So here you'll see there's straight lines in this part of the experiment, but in this part, at the top of the level of the water, the light actually bent towards your eyes. Because of the effect in the experiment, objects underwater appear to be at a different place than they really are. You may have seen this when you've been in a swimming pool. Sorry. You can throw an object into the swimming pool to retrieve, and you can dive towards that object, but it may be a little distance away from where you saw it when you looked at it from above the water. But light does not always refract when meeting an obstacle. Some substances create the incidence that leads only to reflection, not refraction. And an example of this, technical problems here. An example of this is fiber optic cables. In figure 15.8 of your text, they have an example of what it takes to make a rainbow. When white light hits a water droplet in the air, and by the way, you can't have rainbows, you know this intuitively, unless there are water droplets in the air. Now, it doesn't have to be raining hard. In fact, on the contrary, you usually see rainbows at the end of a storm, or when it's just drizzling outside. When white light hits a water droplet in the air, some reflects and some refracts into the water droplet. Since the amount of refraction depends partially on the wavelength of the light involved, this separates the white light into its colors. So here we have white light coming from the sun, and you'll see that you have colors separating, and you have your red on top, violet on bottom. as the refracted light travels through the water droplet, as it continues down, it eventually hits the other side of the water droplet. And at this point, you could see it switch. A portion of the light refracts out of the water droplet, so it actually comes out, but a portion reflects also. And here's the reflection in here. The reflected light travels to the other side of the droplet where some of it is reflected and some refracted. The portion that is refracted has its wavelengths separated even more. So you see the wavelengths, the colors, separated even more than they were than the initial part of the interaction with the droplet. Because the amount of refraction depends in part on the wavelength of light, is the reason that they get more separated. With this second refraction, the light's been separated enough for us to distinguish the colors. This is your rainbow. So your rainbow is a refraction. Notice where the light leaves the water droplet when it, the droplet of water. Here it is right here. In order to see a rainbow well, there must be water droplets in the air, and the sun must shine on the droplets from behind you. The light must be refracted, then reflected, and refracted again to make the color separation strong. Not only does the sun need to be behind you, it needs to be at a certain angle for this all to happen. Now we'll look at the picture again, and you will see that the light that is bent the lowest when leaving the droplet is the red light. So when it first entered the droplet, the red light was on top, but when it leaves, the red light is on the bottom. The red light must come from the highest droplets in the sky to bend the most. In this manner, the violet light comes from the lowest droplets in the sky. So that's how it works. The red light will actually be refracted into being the lowest eventually when we see it, but it's actually the higher, it's coming from the higher water droplets in the air. So hopefully this has assisted you, and it's a little bit of a confusing subject with the reflections and the refractions, but it's just important to know that the refractions actually bend and the reflections don't in the same manner. And we'll talk again in the next video.